Let's say we had a beaker, and in this beaker we had some catalyst or an enzyme and a substrate like glucose. And what we want to do is be able to determine what kind of reaction rate, how quickly the glucose will be consumed as a function of the concentration of glucose that is present. And so what we're going to do is turn to something referred to as Michaelis Menten Kinetics, which allows us to determine the governing behavior of the reaction rate in this process. And so intuitively, we know that if there's no glucose present, there's not going to be a reaction, so we can make a point at 0, 0. What we also know that isn't quite as intuitive is that as we continue to increase the concentration of our reactants, there's going to be an upper limit on how fast our reaction will occur. And this intuitively is because there are finite number of active sites present for the reaction to actually occur. And what you can think is if all the active sites are full, adding more reactant isn't going to make a difference because the reactant can't get into the active site to actually react. And so what you'll find in Michaelis Menten is some upper limit referred to as Vmax. And Vmax is a horizontal line that your graph will eventually reach, a horizontal asymptote. And if you were to actually plot the reaction rate as a function of the substrate concentration, you would see things that look like this. And so this function has the form of the following, where V, the reaction rate, is equivalent to Vmax times your substrate composition or concentration divided by the Monod constant Km plus your substrate concentration. And what I want you to see from this is the initial and terminal behavior. What that means is as S is small, in other words, when S is a lot less than your Monod constant Km, which I'll get to in a minute, what we're seeing is that V is about equal to 1 over, it has a slope of 1 over Km. It's a constant slope. What that means is we're seeing a line in this initial regime of our Michaelis Menten plot. Now, looking at the terminal end of our plot, what we're finding is that as we continue to increase S, as S becomes much larger than K sub M, V equals Vmax, which is what we would intuitively expect given the finite number of active sites. Now, what we also can deduce from a Michaelis Menten plot is K sub M graphically. And the way we do that is we look at where the rate is equal to 1/2 Vmax, and we read off what the substrate concentration is. So when V equals 1/2 Vmax, the substrate concentration is equal to K sub M. This is called the Monod constant. And the Monod constant has the same exact units as your substrate concentration, and therefore K sub M will have units of moles of S per liter of your solution. And so this wraps up an introduction to Michaelis Menten Kinetics. And what I'm going to do in a follow-up video is go over how we can model the different types of inhibition that we can expect to find. And so I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.